Your colleagues join in a while. So today we are going to talk about the final algorithm, PPO. Okay, not that doesn't mean that this is the last algorithm in RL paradigm. No, in this course we are doing the foundational algorithms. Right? We did DDPG, we did TD3, we did SAC, and now we will be doing something called PPO. Okay, which is Proximal Policy Optimization. So from the name here, you understand that it has to do something with things being close to each other, right? That's what proximity stands for. Like you're closer from, literally this word proximal means something that is closer to the center, okay? So here also, it has to do with your old and new policy, okay? Now, what is the ultimate goal of reinforcement learning? Maximize, right? Maximize the expected return that you have over the entire episode horizon. Okay? You do that through different methods, right? You do it either through the value optimization method, the value-based methods, right? Where you have two stages, first stage value iteration, policy iteration, then policy improvement. Or you can directly do it through the policy improvement itself, which is also called as policy gradient method, right? Here you are trying to tune the actions such that you always increase the probability of taking actions that leads to higher returns, right? That is policy gradient. Now PPO is a policy gradient method, right? Up until now the other methods that we studied, DDPG, TD3, SAC, which are nothing but basically one built on top of the other, okay? However, PPO is a parallel algorithm. It's a different algorithm, parallel in the sense it is parallel to the other algorithms that we studied, okay? Like you built TD3 based on DDPG, and based on TD3 and DDPG, you built SAC on that, right? So basically those are building blocks, DDPG foundation, TD3 first floor, SAC second floor. This is a different building altogether, okay? Those were actor critique paradigm based algorithms, right? So you had both actor and a critique, implying that you did the policy improvement part, policy gradient part as well, where you increase the probability of taking the actions that led to maximum returns or higher returns, and at the same time you also did the value computation. So they were basically working hand in hand. Value evaluation was done based on the policy improvement that was done, and then they talked to each other, the actor and critique that is, and that we had it in structurally through giving the output of the actor to the critique, right? In this one we do not have that. We are directly working on the policy improvement part. So we directly worried about improving the probabilities of those actions that leads to higher returns. Okay, so therefore it is a policy gradient method. Okay, in policy gradient methods that you studied earlier, you studied two policy gradient methods. Remember, algorithms. Remember, what were they? What were the two policy gradient methods? Sorry? Reinforce. Right? No. Off policy, on policy is the type of method that you use. Right? Okay. You also had actor critique, asynchronous actor critique, and advantage asynchronous actor critique. Right? A3C and A2C. Right? So in that, you remember you had something called an advantage function, which was the difference between the actual value function computed and the actual reward function that you will get in reality, right? Based on these differences, you did the policy gradient part, right? If the action was advantageous, that is, if you got a higher return than expected, it means that you are at an advantage, which was mathematically signified by the advantage function being positive, and then correspondingly you increase the action probabilities of those actions. Right, probabilities of those actions rather, okay? So here you have the same thing. However, when you change these policy gradient probabilities, okay, the action probabilities, they are very sensitive to noise. In the sense, say you have this as a plane of actions, okay? This is, say, a plane of actions, okay? On the surface, say that you have a line, it's a 3D surface, okay? Assume this is a 3D surface, and these are these are coming up and these are going inside the surface of this plane. Okay. The actions here, assume this region that I'm highlighting is an infinitesimally small area. Okay, very small area. Okay, say the difference between the ends of these actions, these are action lines. Okay, is not even 1%, less than 1%. Okay, the difference in action within that zoomed in part. Okay. Now physically, for physical robots, you know that if you change the action by less than 1%, your output should not change much, right? Be it a flying robot, be it a ground robot, be it an exoskeleton or a humanoid, whatever you have, right? Within a certain action range, the output range will be within a certain range, right? This implies that a small change in action cannot lead to a drastic change in the output action that you get, right? However, that is a different thing, that if you are right at the cliff and one small motion, you fall off the cliff, that is the consequence of the action that you are getting. But the motion, the physical motion that the robot undergoes, say even if it is at a cliff, okay, if you change the action, you are giving it, say, left command. Okay, and if the action now, you're increasing gradually by less than 1%, 0.5% every step. Okay, so the robot should move very slowly, like, right? Like now if you say it to move left and it is moving at this rate and you do not change the magnitude of your action, okay, you simply, even if you change the magnitude, it is less than say less than 1%, say 0.5%, okay, change in action. Your robot should move very small distances. Right? So that means that these two actions that you're giving more or less should have a same value function, right? Which is the action value function, implying that if you are in this matrix, you have this matrix, you remember, you have the S and A's, states and actions, right? For a very discrete robotic environment or a continuous environment is nothing but a highly, infinitely discretized, discontinuous world, grid world, right? So here between any two lines, you should have infinite different discretizations, right? So within this action space, if you know that you are at this state and this action, taking this state and this action should not drastically change your reward function, right? Are you clear on this part, right? So when this change is very small, it should also reflect mathematically in the value function, right? When the value function change is small, it also ties to the advantage function, right? Because advantage function is nothing but your value function minus your reward, right? So when this change is small, it is reflected in the value function. When the value function change is small, the advantage computation is small. When the advantage computation is small, the signal of changing the reward or the action probability is small as well, which would in turn imply that the new policy that you are getting is not drastically changed from your previous policy. Also, it can mean that your policy changes are not overreacting, right? Now say suppose if I tell you to go work hard, okay, that doesn't mean you will go and study 24 hours. Say now you're studying 6 hours a day. If I tell you go work hard, you will work 8 hours a day probably, but not 24 hours a day. That's a huge change, right? You will not do that. You will do 6 to 8, 8 to 9, 9 to 10 maybe, slight changes, right? Or if I tell you, okay, fine, go enjoy your lives, that will not make you go from 6 hours study to 0 hours study. Well, that can happen, I think, but that shouldn't happen, right? So it should go from maybe 6 hours to 5 hours, right? The changes in your policy should be small, right? We don't want drastic changes in policy. We don't want overaction or overreaction to policy changes, okay? This is one thing. Keep this in mind. Now, remember the policies that we are getting, okay, if they are stochastic policies, they are probability distributions, right? They are probability distributions. If you have stochastic policy output, okay, and PPO, as a matter of fact, is a stochastic algorithm. It's on policy, we'll talk about it as well, and it is stochastic, okay? What was DDPG? Deterministic. That is, for this state, if you are in this state, you have to take this action, that's it, right? However, PPO will give you a distribution of this actions, that if you are in this state, most probably take this action, however, you can take this or this actions as well, okay, with a slightly lower probability. Fine, right? Now, in deterministic settings, okay, you could simply take the difference between your current action and the next action, and you will know how different those actions are, right? Like you are in a given state, you take the difference between the two actions, numerically you can simply say subtract for that matter, okay, in a very raw sense, okay. You simply subtract and you will get the difference between the two actions. Say if the actions are very simple magnitude actions, numbers, okay, you will get the difference which says, okay fine, this, if I'm in this state, one time my policy tells me to take this action, the other time it tells me to take this action, right? So now you have a difference, you can compute the difference. However, if you have such kind of probability distributions, you cannot simply perform arithmetic subtraction here, can you? So you will have to compute the difference between the two distributions in some other way, okay? There steps in a method called KL method, okay, which again stands for some hard to pronounce names. So it's an abbreviation basically for Kullback something. Let's just keep it KL for simplicity, okay? So it is KL divergence. It is also called KL divergence, okay? What that stands for is when you have two probability distributions and you want to compute the difference between those two, in a sense a difference, okay? It's basically a measure of difference in two distributions. So when you want to compute that, you will use KL divergence, right? Okay, now why did I tell you about KL divergence? Because KL divergence plays a significant role in PPO algorithms, right? So now you know two things, that first, you do not want your policy changes to be drastic, right? Because even when you are learning, okay, so this is particularly useful during the training phase, okay, because anyhow after you have learned, you will get a good policy, right? All these things that you do, the changes in the methods that you are studying about is to improve the training of the RL algorithm itself, right? Because at the time of implementation, anyways, you have to make it deterministic. Even for a stochastic policy, you have to make it deterministic, right? Because in real world, you cannot tell the robot that, okay, fine, if you are in this state, take any action from this probability. No, it doesn't work that way, right? At that time, it has to be deterministic, that, okay, fine, if you are in this state, take this action, that's it. During the training phase is when all these things matter, right? So what you're trying to do is you're trying to clip the changes of policies between one iteration to another. Clear? What did you understand? What are we trying to do? What's the main objective now that we are trying to achieve? Are we trying to increase the difference in the policy between one step and the other? No, then? Sorry?
We want to control the changes, neither too fast, neither too slow.
Yes, we want to control. We want to, no, we don't want it too fast. That is for sure, okay? Small changes are fine. So we are clipping it so that the change in policy between any two iterations is small. Cool? Clear? Okay. So that's what we are doing. Too small, slow learning, hence we need some kind of too large policy changes very drastically, right? So we want something in between these two. Okay? Okay. So basically, you have a small something called a trust region. Okay? That is, you want your policy changes to happen within that region. Okay? When you are moving from one iteration to another, okay, and you have a policy which gives you certain set of actions, action state mapping rather, you move if you are within that area, and the learning happens that way, right? Like when you are in a small subset of the entire environment, you perform certain actions there and then you move on to next states, right? So when you are performing these actions, you want to make sure that you are within a small trusted region, okay? This region is called the trust region, so that your changes are confined within this trusted range, right? It doesn't change too drastically. Clear? Clear? Okay. Okay. This gave birth to another algorithm, RL algorithm, called TRPO, Trust Region Policy Optimization. Okay. This is a predecessor of PPO. Okay. However, this did not gain much traction or much popularity in common applications because of certain reasons that we'll talk about now. Okay. And PPO very efficiently addresses those shortcomings. Okay. So in this TRPO, what you do is you take something called a ratio here. Okay. This ratio is basically the KL divergence between the current policy and the old policy. Okay. Here you take it in terms of ratio, okay, and then you multiply it by the advantage function, and that's just for improving, okay. But however, this is the most important part here, the change here, the ratio here, okay, this ratio between the current and old policy, okay. Now you are doing this, so what are you doing? You are maximizing the expectation. Right, you're maximizing the expectation, which is the goal of any RL algorithm, that is. So this is maximization of the R reward function scaled by the advantage, basically, whether you want to do it or not, positive or negative, okay. However, this maximization, okay, which is an optimization problem now, is subject to certain constraint, okay, and this is a hard constraint, okay. That is, when you are performing that optimization, you have to make sure that at every step, this given constraint is fulfilled at every step. Okay, this is what is called constrained optimization. So you give an optimization problem with certain constraints, with certain rules, basically. Okay, clear? Are you clear up until this point? Everyone? Sure? Okay. So here what you are doing is performing the optimization, which RL should do and RL has to do, but with a constraint here, okay. Here you are giving a hard constraint that the KL divergence between your old and new policy should be less than a certain threshold, okay. KL divergence in a raw sense is nothing but the difference between two probability distributions, okay. So you are trying to say here that the KL divergence between the old and new policy should be less than a certain threshold at every step or every iteration of the learning. Clear? Okay? Yes?
If it does not satisfy this, then the new policy is ignored and we go to the next step?
Sorry?
If it doesn't specify the KL condition, so it ignores this new policy and then goes to...
No, it will redo that step again.
Okay.
It will have to redo that step again, okay? It will not only... That's the whole point of a hard constraint, of a constraint optimization problem, that it will not do things that will not satisfy the constraint, right? It will perform extensive computation so as to make sure that the constraint that you have given is respected, okay? So this, you understand that this is a hard constraint, right? And constraint optimization problems are computationally very demanding, okay? So the learning by this method will be slow, right? Plus a lot of computation will be required, because as the dimensionality of the problem increases, right, that is, as you move to more complex problems, this computation of KL divergence will become complex, okay? However, when you are performing the optimization with that constraint, it gets super difficult, right? So the learning becomes very, very, very slow, okay? However, you are making sure that yes, the policy is not changing a lot, you are achieving your objective, but in a very inefficient way, okay? Clear? So yes, because it's an optimization problem, you know there are matrices involved. So matrices with constraints, you will have to compute inverse of matrices. And inverse of matrices is something that is one of the most difficult computations even today, with all the computation power that you have, because AI mostly, well, not mostly, some part of AI is, or significant part of AI is computation of inverse matrices, right? And when you have these huge matrices and you have to compute the inverse of those without getting into singularity, it's very, very difficult. It's computationally very demanding, right? So yes, good thing is you make sure that the policy does not change much, okay? Plus, given it's a hard constraint, you will always make sure at every iteration that it never violates that constraint. So at every point, yes, the policy change is small, okay? Mathematically proven, it is small, okay? However, with disadvantages comes the disadvantage of computational burden, right? You don't want that to happen. And it becomes, so there is second order optimization, which is difficult, okay? So you don't want that to happen, right? So you want the advantages of TRPO, that is, you want these advantages of slow or restricting the changes in policy, but without the math, okay? Without the complicated math. And there steps in PPO, okay? So what PPO does is, it does limit this change, because you remember this constraint that we had, it computed the KL divergence between the old policy and new policy within, and it subjected it to a constraint that it should be less than a certain threshold delta, right? A mathematically formulated hard constraint, right? Now you don't want to give such constraint to the optimization, but at the same time you want that effect of clipping the policy changes, right? PPO does exactly that. Okay, it does by two methods, one through a clip surrogate objective function, the other through KL penalty methods. Okay, KL penalty methods is not used a lot in general in literature because of the ease of using of the clipped surrogate function. Okay, that is one of the most implemented PPO algorithms for any application for that matter, not only robotics. Okay, so here again we have this ratio. You remember even in TRPO we had this ratio between the policy, new and old policy, right? You have that policy. Now what you're trying to do is your loss function, okay, will tell you that you get the expectation, you have to take the minimum of either this ratio multiplied by the advantage function, obviously, minimum of, okay, either this ratio, or you clip that ratio within 1 minus epsilon or 1 plus epsilon, right? I'll show you a graph in the next, I'll show you a graph now, wait. So what you're trying to do is, you are making sure that the changes within this region happen as is, okay? Like this is a linear region. There is no clipping within this region. However, if the change is more than this one, that is the change is here at this point, then it will clip it to a flat region, this one, right? This is what you're doing through the clipping function. You're like the changes should lie on the blue line only, okay? So within this red region, okay, anyways this is a linear region, so there is no clipping happening, okay? You remember you had, remember that graph, okay? So you have this clip function, you're taking the minimum of either the actual policy change or the clip policy change. Clip policy change will tell you that if this ratio is greater than a certain threshold, then change it if it is decreasing only by 1 minus epsilon, or if it is increasing only by 1 plus epsilon, right? So you basically take the smaller of these two values, and that will be your loss function that you're trying to improve, right? So here you have the constraint, but not in a hard way, it's a soft constraint, but it is designed such that it will always be respected, right? And here you don't have any matrices to take inverse of, because this is not an optimization problem in that sense with a constraint, right? Clear? Are you all clear? Sure, 100%? Right? Okay. So this will ensure, like I said, that the updates are within a certain range, right? Earlier we called this region as a trust region, right? So now here that policy, that algorithm was called TRPO, Trust Region Policy Optimization. This is Proximal Policy Optimization, an advancement of TRPO where you have all the advantages of TRPO without the math involved, implying less computation. Clear? Right? Okay. So again, see, if the ratio that you have is greater than 1, it means that yes, the new policy is better, take that new policy. If not, do not take that policy. If it is 1, it means your new policy and old policy are same basically. This is the clipping range that we defined, 1 minus epsilon, 1 plus epsilon, right? If it is either to be decreased by that much or increased by that much, cap it any which ways, right? So we get PPO that enforces this trust region in a soft way. Okay? Clear? 100% clear? Okay. Yeah, this we already talked about, right? Like we change the policy when the advantage is positive. We do not change the policy, or rather we reduce the probabilities of the actions if the advantage function is negative. Increase if the advantage function is positive. No change if the advantage function is 0. Okay? Yes, here you can see that when you change the policy, within that red region it is linear. That is, the changes within that red region are allowed. Beyond those red regions, you will clip the changes. Okay? You're like, no, even if the policy tells you to change more, you're like, no, that is not a good way to improve things. Let's do it slowly. Okay? That's how PPO works. Clear? Yeah, here it is. This is another form. So there you had the clipped surrogate objective where you were clipping the, the changes in policy explicitly. Here you compute the KL divergence, okay? And this is the RL objective function that you have where you have to maximize the expectation of the expected rewards. Now here within this expected equation you add this constraint, okay, of the KL divergence methods, right? This is again in a way TRPO, but again soft way, because here the constraint is not, it's an optimization but without the constraints basically. Yes?
What is the difference? I don't see a lot of difference between this part of the TRPO.
Yeah, that's why there is not a lot of difference.
How it's solved in this one?
Okay, because there the constraint that you had was a hard constraint. You had to follow it always. Here, this is within the objective function. So within the objective function, you have to, one is plus, one is negative. So basically, you simply have to balance it, right? It isn't a hard constraint that, no, do it only this way. No, do it such that you maximize that objective. That's what we are telling now, okay? However, this implementation of PPO is not very common. It is the other implementation, right? The clip function that we use is what is more common. Yes, somebody called me? Oh, okay. So why does PPO work so well? Because first, you are limiting the changes in policy, implying you get a stable learning, okay? Also, you do not have a second order optimization, constraint optimization problem at your hand now, right? It's a much softer first order optimization. So you don't need to compute inverse of matrices, or you don't need any special solvers, right? It is a lot easier mathematically and computationally, okay? And yes, you can reuse collected data for multiple gradient steps. Okay, what you do is you take the same, it is on policy by the way, okay? So you cannot take samples from a buffer because you don't have a buffer to begin with, okay? However, with one set of samples, you perform the gradient update step that you have multiple times, okay? With that same samples. And once you perform any computation with a given set of samples, you throw that samples away in on-policy. You do not store it anywhere. You do not even have a storage house to store to begin with, right? Now, if I tell you to keep something or store something, you need to have a place to store that. If you don't even have that place, you're never going to store it, right? So that's happening here. Okay. Yes. This, because of all these advantages, this is one of the most used algorithms. Well, yeah, one of the most used algorithms when you have on-policy application, or yes, when you want to use on-policy methods. Okay. Yeah, this is just the theoretical foundation, gradient. Okay. Yeah, this I already explained. Okay, here the advantage function that you compute itself. Now remember, advantage function can be computed in two ways. One, through a Monte Carlo approach, where you run the entire episode from that state with a given policy, and you subtract the rewards that you got actually, right? And the other is through TD approach, where you take one step only and remaining you bootstrap, you estimate, right? So now you're trying to, because PPO relies so heavily on the advantage function, right? You want a good estimation of the advantage function, right? So you do not want a completely bootstrapped estimate, nor can you perform actually a full episodic returns, right? So you want somewhere in between, right? You want to have, say, 6 steps or 10 steps or 100 steps, but not 1000 steps, right? So this balance between variance and bias, right, where you are trying to reduce the estimation part, but at the same time reduce the computational burden of computing the entire episode as well. So when you are trying to balance that trade-off, then you get something called a generalized advantage estimate. Okay? Yes.
This has the idea of TD1 and 2 and 3.
Exactly. Yes, exactly. So this is basically TD estimates, but you remember what we studied was TD0, implying that is one step only. You take one step, you bootstrap everything, right? This is TD lambda basically, where you have lambda for n steps, okay? 1, 2, 3, 4, 5, whatever steps you want. Not the entire episode, so you are balancing what? The computational requirements and the estimation requirements, right? When one goes down, the other goes up. When the other goes down, the first one goes up, right? Clear? Okay? Okay. Now PPO compared to other similar algorithms, all of them are on policy A2C, A3C, okay, or TRPO. Stability, A2C and A3C, very unstable, right, because the policies can change drastically between any two iterations, which would in turn make the learning slower because you're going back and forth, back and forth, back and forth, okay. TRPO, most stable, super stable, but comes at a cost of computation, okay. PPO is almost that stable, okay, but without the computational burden, okay. However, there will obviously be a slight trade-off in the stability. It will not be as stable as TRPO because you don't have a hard constraint here, right. Complexity, significantly in order of magnitude difference probably in the simplicity that you have between TRPO and PPO. TRPO is super complicated to implement, PPO not so much, okay. And yes, computation you already talked about, practicality, okay. Now PPO compared to other off-policy methods like DDPG, TD3 or SAC, okay, you have in DDPG and TD3 you have deterministic outputs, in SAC you have stochastic, in PPO you have stochastic only, okay. On policy, off policy we already talked about. There you are trying to use target networks, entropy injection through the methods to stabilize the learning and improve the learning. Here you are trying to clip the changes in policy. Again, they are very suitable. They are not the only suitable algorithms. Keep this in mind, okay? Explore everything, okay? However, depending on the application that you're trying, you have at hand and many other constraints, obviously the computational requirements, the efficiency, the speed, the accuracy that you want, decide on the algorithm, okay? However, generally, not a hard and fast rule, but a generalizable statement is that for continuous control, which are most of the robotic applications that we do, DDPG and its family is very good, Okay. However, if you want to have learning on the physical setup itself, like say suppose you have a robotic arm, okay, you have thousands of robotic arms, okay, and you want to learn a pick and place operation on them on the physical hardware, then PPO is better. Okay. Why? Because you are clipping the changes, so therefore there is no drastic changes in the policy, so in turn not drastic changes in the action, so it is safe in terms of the physical world that you are trying to learn, right? Also it is on policy, so that gives it an advantage of implementing in real world, right? However, you can almost certainly not use real-time hardware learning on UAVs, for example, which are inherently unstable systems, right? But robotic manipulators are slightly more stable, right? They at least don't fly around, right? So that is why you can probably use, but even they are expensive, right? And you might burn the actuators when you are doing the learning on the hardware. However, there are certain places where this is happening, where they have thousands of robotic arms in one place, and they're trying to do it on the hardware itself directly for extremely extremely precise operation and performance. Okay, so that is that for PPO.